Hello, everyone. My name is Rostyslav Serha, and I will use this opportunity to present my latest research findings to you here on our Nanomag YouTube channel. Earlier this year, we published a paper titled Magnetic Anisotropy and GGG Substrate Stray Field in YIG films down to millikelvin temperatures in the peer-reviewed journal NPJ Sprintronics. In this manuscript, we discussed the influence of the gadolinium gallium garnet substrate on the FMR frequency in YIG films at low temperatures and explore the insight that this offers. For a start, I'd like to explain why we are focusing on magnonics at millikelvin temperatures. A couple of years back, a significant review paper introduced a new and vital chapter titled Towards Quantum Magnonics. It highlighted that most quantum magnonics experiments and devices necessitate working with single magnons or on a single magnon level. Due to the bosonic nature of magnons, we must adhere to the Bose-Einstein statistics, and this requires us to reach ultra-low temperatures in the millikelvin range. This is necessary to effectively reduce the thermal magnon population and making it feasible to isolate and manipulate single magnons. We managed to achieve these conditions with our advanced equipment. For sample characterization and various measurements down to 1.8 Kelvin, our team utilizes a physical property measurement system, short PPMS, and we primarily employ the system for vibrating sample magnetometry, VSM, and ferrimagnetic resonance spectroscopy, or short FMR, which can operate across a broad frequency range up to 40 GHz. Another important system is the blue force dilution refrigerator. This cryostat allows us to cool samples down to 10 millikel. It is equipped with a superconducting vector magnet, enabling us to apply bias fields in any direction. And with this sophisticated setup, we are now capable of conducting FMR measurements and propagating spinwave spectroscopy and at ultra-low temperatures, even up to 70 GHz. Yttrium iron garnet, or short YIG, is a material extensively utilized in magnonics due to its minimal magnetic damping, which allows magnon lifetimes to extend up to 1 microsecond. This property makes YIG highly suitable for experiments in magnonics as a model material. However, as we transition towards future magnonic devices, there is a necessity to miniaturize component to the nanoscale. Consequently, the field frequently employs thin YIG films grown on paramagnetic gadolinium gallium garnet substrates, short GGG, and these samples are used in a study, and we use this in our studies. And I'm going to present today was a 100 nanometer YIG film grown in the 111 direction on a 500 micrometer GGG substrate. The sample has a square shape of 5 by 5 millimeters. The paramagnetic nature of GGG substrates presents a challenge. At low temperatures and under sufficiently high magnetic fields, the paramagnetic system becomes ordered and magnetized, exhibiting a saturation magnetization several times greater than that of yttrium iron garnet itself. This magnetization of the substrate generates a non-uniform stray field around it, as you can see in this small visualization. For instance, in in-plane magnetized YIG film, the stray field from the GGG reduces the internal field of the YIG. Here is a vibrating sample magnetometry, VSM measurement, that shows the scale of the GGG magnetization at low temperatures. These VSM measurements show that the GGG substrate can be significantly magnetized using moderate magnetic fields, such as 1 Tesla. It's the green line, and at 2 Kelvin, we already reach around 400 kilaampere per meter. Recently, our research has focused on the impact of the homogeneous stray field created by the magnetized GGG on the FMR of yttrium iron garnet films. We have been particularly interested in understanding the mechanism by which GGG-induced damping occurs and how it increases in YIG films and structures. This animation will clearly show what's happening in our experiment. At room temperature, the GGG substrate is paramagnetic and barely responds to an external magnetic field oriented in the in-plane geometry, allowing us to measure the YIG FMR using the antenna without any problems with common broadband strip-line spectroscopy. However, at low temperatures, the GGG is easily magnetized by the bias field. It then becomes a source of stray magnetic field, and as you can see, it points in the opposite direction to the external magnetic field, lowering the internal field of our magnetic medium inhomogeneously. The inhomogeneity is clearly visible in this simulation of the sample that we use in our experiments. It shows the stray field created by a 500 micrometer GGG substrate beneath the 100 nanometer YIG film. This field is remarkably non-uniform, leading to a frequency shift in the FMR. And as different areas of the sample encounter varying field strengths, they resonate at different FMR frequencies, impacting the overall shape of the FMR, leading even to an inhomogeneous broadening. The effect of the GGG stray field on the frequency shift in yttrium ion garnet films at low temperatures is always visible and has been noted in previous studies before. However, only one prior paper, this one, accurately interpreted this behavior as a change in the internal field due to the GGG stray field. The paper was already published in 1987 by scientists from Ukraine in Kiev. But previous measurements were limited to 4 Kelvin and only a single frequency. Our research significantly expands these parameters, providing new interesting insights. And the most important is that we can now obtain values for the true magnetic anisotropy of our YIG films at low temperatures. Also, we can by this explain the observations that were already published in previous papers, but mischaracterized. Here you can observe some example spectra from our measurements. Notice how lowering the temperature not only affects the frequency, but also significantly alters the shape, width, and amplitude of the spectra, especially noticeable at 2 Kelvin. The frequency of the FMR in an in-plane magnetized YIG film is governed by the Kittel formula. For our specific analysis, we incorporated the anisotropy fields here into the magnetization part of the formula and a stray field from the GGG substrate into the bias component of the formula. Our approach involves measuring the FMR frequencies and calculating the theoretical saturation magnetization of YIG at various temperatures. Additionally, we analytically determine the stray field of our sample, knowing the magnetic field of GGG, here noted as BGG, at any given field and temperature. However, the anisotropy and geomagnetic ratio gamma for this 100 nanometer thick YIG film at low temperatures remain unknown. Therefore, we use these parameters as fit variables to analyze our FMR frequency data by performing the so very known Kittel fit. The graph on the right illustrates the impact of the GGG stray field. Without considering the GGG field, the FMR frequency would follow the trend set by the increasing saturation magnetization. So it would, from room temperature, increase to higher frequencies as a saturation magnetization increases at lower temperatures and stay constant after around 50 Kelvin. However, as the GGG becomes magnetized, it diminishes the internal field and causes a downward shift in the frequency. The stronger the external field applied, the greater the magnetization of the GGG and thus larger the frequency shift that can be seen for these three different external magnetic fields. From the Kittel fits, we derive these values for the effective anisotropy, which increases as the temperature decreases. Notably, the anisotropy increases increase is more pronounced in the 112 direction than in the 110 direction. Meanwhile, as shown in the inset, the ferrimagnetic ratio gamma consistently decreases with temperature regardless of the magnetization direction. This effective crystallographic anisotropy consists of two main components, cubic and uniaxial anisotropy. To accurately determine these, we fit the FMR frequencies for both directions using two separate Kittel equations, one for each direction, as you can see here above the second graph. Our results reveal that the cubic anisotropy more than doubles and saturates at low temperatures, while the uniaxial anisotropy changes sign and also shows a high increase at low temperatures. Now let's examine the behavior of the GGG induced magnetic field across the temperature range in the middle of the sample. The measurement points are derived from rearranging the Kittel formula to isolate BGG, the field of the substrate, and we observe that for solid points there is a perfect overlap with our calculations, confirming the high accuracy of our fitting parameters. For the hollow points measured in the dilution refrigerator, we can directly calculate the GGG stray field as we do for PPMS measurements, because our magnetization measurements of GGG only extend down to 2 Kelvin. Therefore, we do not perform the Kittel fit for these points. Instead, we use anisotropy values from 2 Kelvin, assuming they do not vary significantly at lower temperatures down to 30 millikelvin. We then compare these with the theoretical predictions of the Brillouin function, which we use to extrapolate the data from 2 Kelvin down to 500 millikelvin and 300 millikelvin. Through the magnetization, we can calculate the stray field. As depicted, the GGG stray field increases at these lower temperatures as the GGG becomes more easily magnetized, leading to changes of up to 40 millitesla in the internal field of the yttrium ion garnet. This is shown by our measurements. Interestingly, there appears to be no difference in the magnetization behavior between 300 millikelvin and 500 millikelvin, contrary to the predictions of the Brillouin function that is depicted here in these dotted lines. This observation is, however, consistent with existing literature where the magnetization of GGG is measured via magnetometry of pure GGG and shows similar behavior for temperatures below 500 millikelvin, as we can see here in the paper of updating the phase diagram of the archetype of frustrated magnet like GGG. Everything below 500 millikelvin here, like 340 down to 80 millikelvin, shows the completely same magnetization behavior, which leads to the same stray field, as shown by our measurements. In conclusion, the results from our latest paper demonstrate the significant impact of sample geometry to determine magnetic properties at low temperatures. Furthermore, as the GGG magnetization notably increases, yttrium ion garnet line widths at these temperatures also increase. Our goal to move forward is to identify the specific contributions to this increase in damping, such as non-uniform field effects, dipole or exchange coupling with GGG spins, microwave absorption by GGG, and impurities in yttrium ion garnet. Understanding these mechanisms will guide us in mitigating these adverse effects for magnetic applications at ultra-low temperatures. Thank you for your attention, and check out the other educative videos about Magnonics on this channel. Bye.